All right, back to strengths of acids and bases. So the strength of the acid is determined by the concentration of H3O plus, which in turn is dependent on the position of the equilibrium that the acid is in. A strong acid is defined. Okay, this is important. Strong acids and weak acids. A strong acid is defined in which the position of the equilibrium is so far to the right that it's 100% dissociated or product formed. Okay, it's not technically. If you went to enough sig fig decimals, it's not quite 100%. But because most of basically all the calculations we do are 2 to 3 sig figs, we can consider it to be 100% dissociated. Okay, so HCl is a strong acid. If you put it into water, note I don't have an equilibrium here. I just have a little arrow. Okay, it dissociates 100%. It dumps the proton onto water. You get H3O plus and Cl minus. Okay. In our data booklet, if you look in your data booklet and you go to, this is going to be your best friend for this unit. Some of you are your only friend. Ooh. This page, the relative strengths of Bronsted-Lowry acids and bases. They are highlighted. All right. These are all the strong acids. We just say the Ka is very big. All right. Because for all these sig fig calculations we do, it doesn't matter. All right. They ionize 100%. So if I put 5 molar of hydroiodic acid in there, I get 5 molar of protons. Okay. That makes sense? And notice they're all arrows. And these ones, does yours have the square box thing, or does it have an actual equilibrium? It has an equilibrium? I don't know why mine has a square box thing, but that's supposed to be an equilibrium. So these are all equilibriums from then on. Okay, and then they have Ka values, which is just like a Keq value, but they put an A beside it because it's an acid, just like Ksp. Okay, and they go from strong up here to weak down here. Okay. Lesson over. Yeah, go home. Okay, weak acids do not dissociate 100%. Therefore, they are in equilibrium. Okay, and they have an equilibrium constant that we call an AA or Ka for acid. HF, hydrofluoric, is considered a weak acid. All right. When it is put into water, we have to put the equilibrium sign. We get H3O plus, if I could write, plus F minus. And I guess technically we should write aqueous. But, and what is the equilibrium constant for? Oh, 6.7 times 10 to the minus 4. We might as well look it up. HF. Where's HF? Does anybody see HF? Yeah. Oh, right. 3.5 times 10 to the minus 4. Apparently my pen doesn't want to work on here. There it is. Yeah, 3.5 times 10 to the minus 4. Thank you. Ka equals 3.5 times 10 to the minus 4, which is not a very big number. So basically means less than 1% of the HF will dissociate. Okay, so it's not very much. Okay, so then when you look at some of the other weak acids, like water is a special one, but peroxide, H2O2, hydrogen peroxide, 2.4 times 10 to the minus 12. So like minute amounts will actually dissociate. Okay. Okay. What is H3O plus and what is H plus? In most chemistry books, you're going to see H plus written. You're going to see stuff like the equation that I just wrote. If you put HF in water, and I will do this too, usually we write that. So what's the difference between H plus and H3O plus? All right. You shouldn't write that. Technically, H plus does not exist on its own. Okay. Because it's very small. It's got a high charge. It's just a proton, which is essentially the nucleus of a hydrogen atom. That's all it is. So it's not going to hang around by itself. Anything that has a charge on it, a negative charge, it will be attracted to. All right. And we know that water is polar. What does polar mean? It's got partial charges, right? So water looks like this. It's got partial positive there, partial negative on the oxygen, because the oxygen is more electronegative than the hydrogen, so it pulls electron density towards it. So if there's a proton floating around, it is going to be like boom and attracted to that. And when it does, that's how you get H3O plus. Okay. So you never really see protons just floating around, but the equation is always written. I shouldn't say always. A lot of textbooks, and your data package does this too. Writes it this way. So why do they do that? Because it's easier. That's basically the only reason. Okay. You just have to understand that this H plus is actually H3O plus in reality in water in an aqueous solution. Okay. Okay. Ternary acids. What does that mean? What's tertiary? 3. It means it has 3 elements. Okay, we got 3 elements. We got hydrogen, sulfur, and oxygen. Okay, what's a binary acid? 2. So HCl is sort of the common one. HF, HBr, blah, 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 blah. All right. Ternary acids differ by the number of oxygen atoms, usually. All right. So you have H2SO4, which is, what's the name? Sulfuric. Which H2SO3? Sulfurous. We got HClO4, HClO3, HCl, blah, 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 blah. Okay. Basically, it's the number of oxygen atoms. So, within a group, H2SO4 versus H2SO3, which is the stronger acid? Any guesses? Sulfuric. The one with more oxygen atoms in general is the stronger acid. And I'll tell you why in a second. Okay. So within a group. So if you have this group, HClO4, HClO3, blah, 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 blah. Which one's the strongest? Which one's the weakest? Strongest, most oxygens, weakest. Now, that's a relative strength. It's not saying that HClO4 is stronger than H2SO3. Those are different acids. But within the group, if you start to add more oxygens, you get a stronger acid. And I'll tell you why in one little sec here. So within a group, the more oxygen atoms equals stronger acid. Okay, why is that? Does anybody have a clue? Guess as to why that would be? Well, an acid wants to donate a proton, right? You're sort of on the right track. What would oxygen do? What does oxygen do in water? Yeah, it pulls electron density, right? So what happens to the protons in water? They have a partial positive charge. So the more oxygen atoms you put onto a molecule, what happens? They're going to want to grab more electron density, which leaves the protons exposed with more of a positive charge, which means they're easier to take away and be grabbed by something else. Okay? So Because pull electron density away from the H's, hydrogen. I'll just say H's. Therefore, H's, hydrogen, are easily given up. You can see this on the table. I'll show you in 1 second. So because the oxygen atoms pull electron density away from the hydrogens are left with this sort of positive charge, and anything that has a negative charge floating along will just pick it off. Okay? Wait till you copy that down, and then I want to look at the strength of the table. Okay. If we look at our data book, well, you can just look up here. So let's look at, we want to compare something here. Okay, well, we'll do this. Just gotta think of how I'm going to explain this. Well, we can. All right. Here's H2SO4. We know that is a very strong acid. That's a strong acid, so it ionizes 100%. If you go to H2SO3, it is no longer a strong acid. All we did was take one oxygen away. Okay, so we've weakened less oxygen atoms to pull electrons away from the hydrogens, so the hydrogens aren't as exposed with the positive charge. All right, and it has a KEQ. If you take, where's HSO3? Or HSO2, there's not going to be one. Well, what if you could make, you're not going to, if you had H2SO3, if you take even another one away, this doesn't actually exist, so we'll pretend, H2SO4 or H2SO2, there's only 2 oxygens that can pull electron density away from here, whereas in this one, there's 3. So you get this greater pull, so they have more of a positive charge. They're not held as tightly, so the hydrogens can come off. Okay? That makes sense? All right, so more oxygen atoms within the group means stronger acids. Okay. All right. NaOH, KOH. These are not Bronsted-Lowry acids bases. Why not? What's the definition of a Bronsted-Lowry base? Can receive a proton, right? They accept protons. NaOH and KOH, by definition, don't accept protons. That's why they're classified as Arrhenius bases, right? Because an Arrhenius base, when you put it in water, creates OH minus. Now, these are still strong bases, so you just have to remember. Are these on the table? I think they're at the bottom, aren't they? Yeah, not really. Okay. All right. So they don't count as Bronsted-Lowry by definition because they don't accept protons. They're not proton acceptors. What is going on with this pen? But you have to remember, by definition, they are, because they ionize 100%. You put them in water, they turn into NaOH, becomes Na ions and OH minus ions. Okay? 100%. No equilibrium. Okay? We don't worry about weak Bronsted-Lowry bases in this part. We'll do that later on. Okay? Okay, are we okay? All right, ionization of water. So, water can act as an acid or a base. What do you call something that can act as an acid or a base? Amphiprotic. Is that what you're going to say? Perfect. Right? You can accept a proton or donate a proton. Okay? So, because water can accept or donate a proton, water by itself. Oh my God. Can donate a proton to another water molecule. And you'll get that. Or if you don't like the H3O plus version, you can just write it's the same thing. Okay? So, this happens in water. Now, it doesn't happen very often. That's a good thing. Well, we don't want to produce a lot of H3O plus. Okay? All right? And OH minus. It's very low in water. So, water has a special equilibrium constant. We call it the KW for water. Okay? It's way, way over here. It's a tiny number. The KQ, which is the KW, is the concentration of this times the concentration of this. Why do we not include these? Because those are like pure liquids, right? So we don't worry about them. So when you multiply the concentrations of those together, the KW of water, or the KW, you did just say KW, you don't need to say KW of water, because that's equilibrium constant of water. It's just, anyway. Is 1.0 times 10 to the minus 14. You need to remember that number. Okay? What? I don't know. Is it? No, I don't think it is. Is it?
No, it is.
Oh, it is right at the bottom. There you go. You want to see where it is? I'll even highlight it for you. Right where it says water. I know. It's shocking, isn't it? 1.0 times 10 to the minus 14. Look, it's, I don't know. If it's hard to remember, I guess it's hard to remember, but. Okay. A mole? All right. This is very important. It controls how much H3O plus and OH minus you can have in solution. Because everything we're dealing with is in aqueous solution, all the acids we deal with. All right? And the product of the concentrations of these two ions in any, this is important, any aqueous solution can never exceed this number. All right? It just doesn't happen. It can't. All right? So when we increase the concentration of H2O plus, so for example, say I added a bunch of acid to this equilibrium. From your chapter 2 knowledge, what happens? Okay, so this spikes. What happens? Then the equilibrium shifts to the left to balance it out, right? What happens to the concentration of OH minus? It goes down. Okay, so when H3O plus goes up, OH minus must decrease. We're going to use this to do some calculations in a sec here. Okay, so when is a solution neutral based on this? Not quite when it equals to KW, because you could have different ratios that multiply together. When would an acid-base solution, quote unquote, be neutralized? Sorry? At equilibrium? Well, in this reaction, I guess no, because you can shift the equilibrium left and right. Yeah, when these are the same, then it's neutral, right? Because they cancel each other out. All right, so a solution is neutral if the concentration of H3O plus equals the concentration of OH minus. When is it basic or alkaline? What does alkaline or basic mean? What do you have more of? OH. So the concentration of OH minus is greater than the concentration of H3O plus. And it's acidic if reverse. Okay. In all of these cases, when you multiply the concentration of H2O plus times the concentration of OH minus, you always get 1.0 times 10 to the minus 14. All right. So this number is constant, the Kw. So therefore, if we know one of these, we can calculate the other one. All right. This is aqueous solutions, and all this stuff we deal with is aqueous solutions. Okay. In non-aqueous solutions, that's a different thing, but we don't deal with that. Sorry. The ones that we deal with are, and that's the pH scale. So the pH scale is good for aqueous solutions. Well, we talk about the pH scale maybe today, but definitely tomorrow. Use a different formula to calculate the pH because things change. But everything that we deal with, yes, aqueous solutions is everything. Because you're always putting it into water, right? Pure water has this equilibrium. So I add a bunch of acid, which means I'm adding a bunch of this. What changes the Kw? What's the only thing that can change Keq? Are we changing the temperature? So we're just shifting it. So that means this goes left. So this has to decrease. Does that make sense? Okay. So remember, yeah, that's important. Only temperature changes Keq or Kw. And you can actually shift. I'll talk about that someday. This is a endothermic reaction, I think. So if you increase the temperature of water, you actually increase the amount of H2O plus, which can decrease. We'll talk about pH in a sec, but would decrease the actual pH of water. But then it becomes a sort of relative thing because you've also increased that. But anyway, that's a side thing. All right. Math, everybody's favorite. Okay, strong acids and bases. The first thing we deal with is strong acids and bases. So what's the concentration of OH minus in a solution of 0.05, molar HCl? All right. Remember, everything we deal with is in aqueous solution, so it's in water. So I just told you that the concentration, Booth? He should be in Stephanie's room. That's usually where they hang out. It's like a bunch of teachers in there. Yeah. We have this equilibrium. We have that equilibrium. Okay? We just have pure water sitting in a beaker. Then we throw a bunch of this junk in. What's going to happen? Is this acid or a base? And it's a strong acid, right? This is important. The first thing you have to ask yourself is when you get a question, right now they're all strong acids, okay? Which means they ionize 100%. So if I say there's 0.05 molar HCl, if I say there's 0.05 molar of that, how much of H plus do we have? 0.05, right? Because it's a strong acid. It ionizes 100%. So that means I have a bunch of this. All right. So what's that going to do to this equilibrium? It's going to spike this and it's going to shift that way, correct? So the OH theoretically should go down. Okay, let's see if that works. We know that this equilibrium, Kw, has to always be 1.0 times 10 to the minus 14, right? The Kw is equal to the concentration of this, concentration of this, and that has to equal 1.0 times 10 to the minus 14. Okay. What's the concentration of that? 0.05. It's that, right? 0.05. That makes sense? H plus and H3O plus are basically the same thing. We've added a bunch of acid. It ionized 100%, so we know what this concentration is. So I know this has been spiked up to 0.05. So what's the concentration of OH minus? Just divide it off. So we get, or 2.0, sorry, times 10 to the minus 13 equals the concentration of OH minus. You know what we should do? Just for comparison. Okay, hold that number in your head. We know, go back up here, Kw is equal to this, based on this equilibrium. What's the concentration of H3O plus here? We don't know. We can just say X. What's the concentration of OH minus? X. Right? They have to be the same. Does that make sense? Okay. So that means it's like X times X. So what's the concentration of H3O plus and OH minus in just water at whatever the temperature is, 25 degrees or whatever that is? You're going to square root 1.0 times 10 to the minus 14, which is 1.0 times 10 to the minus 7? Yeah. So this is the amount of OH and the amount of H3O plus in regular water. I haven't done anything to it. Torsten wouldn't be happy with me. Okay, this is it in regular water. Then for the question we just did, we dumped in a bunch of acid. And we said that this number should go down, right? We calculated it to be 2.0 times 10 to the minus 13. Did it go down? Went down by a massive amount, right? Because we went from 1.0 times 10 to the minus 7 all the way to 2.0 times 10 to the minus 13, which makes sense because that's quite a bit of acid. 0.05 molar that ionizes, boom, 100%. Okay, is that making sense? Basically, you put it in water, it pushes the equilibrium of the water one way or the other. Okay. All right, H3O plus. Calculate the concentration of H3O plus when 2 grams of NaOH is dissolved in 750 mils of water. So what should happen? I don't know. Looking at the equilibrium, we're adding NaOH. NaOH? NaOH. So we're adding a bunch of OH minus. So what should happen? Equilibrium should go the other way. What should happen to this? It should go down. So you can check that. Let's see if it works. So the molar mass of NaOH is 40 grams. So we have 2.0 grams of NaOH. In 0.75 liters, because I want the concentration He's in Torbaum's room. 1 mole is 40.0 grams of NaOH. So grams cancel. We're left with moles per liter, and that gives us 0.667 molarity of NaOH. 0.67? Is it 0.0? Is it? That? 0.067? Okay. 0.067. NaOH is a strong base. Therefore, ionize or dissociate's a better way to say it. %. So basically it goes NaOH. So if this is 0.67 molar, that means the OH minus is 0.067 molar. And then we throw it in water, which means our Kw is equal to the concentration of H3O plus, concentration of OH minus. Kw is constant. Divide that off, and you should get 1.5 times 10 to the minus 14. So it went way down, which makes sense, right? If it spat out a number that was bigger, like 2, then you know you did something right. Or wrong, sorry, not right. You didn't do it right. You did it wrong. Did I do that math wrong? 13?
Wait, were you following it? Were you following the key?
Yeah, my key is...
It's because you did 0.
I know. 0.66. I don't know how I messed that up. All right, so we're off by a factor of... There, that? I'm good at math. Okay, does that make sense, though? We're just looking at an equilibrium. Basically, that's all we're doing right now. Actually, we're going to do most of this chapter. That's pretty much the whole course, really. Okay, except for redox at the end. Numbers 1 to 6, please. Calculate the concentration of protons, H plus, and OH minus, which results from 75 mils, 0.02 molar HBr, and mixed with 225 mils of 0.15 molar KOH. First thing you ask yourself, are we dealing with strong acids and strong bases? I know Noah is saying yes. Does everybody else agree that we are dealing with strong acids and strong bases? That's the first thing you have to ask yourself. Because right now they're all strong acids and strong bases, but later on they're not going to be. Okay? So HBr is a strong acid. KOH is a strong base. That is important because it means if I know the concentration or the molarity or the moles of each one, then I know how much there are when they ionize. That's why we have to know that. Okay? All right. So what this is saying is we dump, you don't have to draw the picture, I'm just drawing a picture. We dump a bunch of HBr in here. We throw in some KOH. I don't care about the bromine and the potassium. All I care about is the H plus and the OH minus. So you got those two things floating around in there. What are they going to do? They're going to bond to each other, right? They're going to neutralize each other. One of these things is in excess. Okay? We want to figure out which one and what the concentrations of OH minus and H plus are when that happens. There's 2 ways to do it. You can do it with concentrations or moles. I prefer moles, okay, but I'll show you both. Okay, I'm going to do it with moles, and then I'll show you the calculation with concentrations. So, first thing you do is figure out the moles of HBr. We know the volume, we know the molarity. How do you figure out moles? Multiply them together, right? So the moles of HBr are going to be 0.075 liters times the concentration. And that spits out 0.15 moles of HBr, which means, because we all know what a strong and weak acid are, strong acids ionize 100%. So if I have 0.015 moles of HBr, how many moles of H plus do I have? The exact same number, because really it does this, right? So if that's 0.15, then this is 0.15. And that's all I really care about. Do it for, what's the other thing? KOH. We have 225 mils of 0.15 molar. And that's going to spit out 0.03375. Austin's nodding. Okay. Which means how much OH do we have? Same number, right? You don't have to write I'm just writing the dissociation just to kind of reinforce that. I'm not going to do that later on. Because I have this many moles of KOH, I know I have that many moles of OH minus. Okay. 0.03375 moles. Okay. What do we have more of? Acid or base? Base. We have 0.03375 moles of OH minus floating around and 0.015 moles of H plus floating around. So what do we do now? What's going to happen? They're going to neutralize, right? If we have excess OH minus, there's going to be a bunch of that left over. How you're going to subtract these two, right? Because it's a one-to-one relationship. For every mole of this, you need 1 mole of OH minus to neutralize it. Okay? So, excess, and I'm too lazy to write the word excess, so I just put the letters. Excess OH minus equals, come on, 0.03375 moles of OH minus, we're subtracting 0.15 moles of H plus, which gives us 0.01875 moles of OH minus in excess. Yes? Okay. So that means in our beaker, we have an excess amount of OH minus. They all cancel out, but there's still leftover OH minus because we had too much of it. Okay. The question says, I want the concentrations of OH minus and H plus. Well, OH minus, we can figure out the concentration now because we know the number of moles. If we divide by the volume, what's the final volume in this question though? It's 300, right? We added 75 mils and 225 mils. So the concentration of OH minus is equal to the moles divided by the liters, which gives us 0.0625, which would round to 2 sig figs, so 0.063. Do we agree with that? 6.3 times 10 to the minus 2, whichever you prefer. So that's our concentration of OH minus. How do we figure out the concentration of H plus? Kw, right? Because it's in water. So now it's the same type of question you had on the previous page. We're just saying we have this much base to the water equilibrium because all the other stuff neutralized each other out. So this is the excess. So then we do Kw. Come on. Kw equals concentration of H plus, concentration of OH minus. And you should get, is it 1.6 or 1.7? 1.6 times 10 to the minus 13 molar. Does the number make sense? Not sure. Does it make sense? It's because I'm so strong. Does the number make sense? Why? Yeah, thank you. It's because it's so small, right? In regular water, what's the concentration? You did it in one of the questions. -7, 1.0 times 10 to the minus 7. So it went down because we're in a basic solution. Okay. Now, you can do it with molarity, all right? And it has its advantages sometimes. There is the question in molarity. So what I did is I went, okay, what's the concentration of H plus? I used the formula M1 V1 equals M2 V2, or M initial V initial equals M final V final, whatever version of it you want, or C. I see some people put C there for concentration, whatever. So the concentration of H plus, because we're doing the dilution, is 0.2 times 75. You don't have to change the volume because it's going to cancel out anyway. It's just a ratio. So we get 0.05 molar of H plus. You do it with OH minus, you get 0.1125 molar of OH minus. Bigger, right? So you subtract them, you get 0.0625 OH minus. So it spits out the concentration of OH minus right away. Okay? I mean, you did the calculation at the beginning, so it's no difference. And then you just put that into the Kw and you get the same thing. All right? Now for that one, it's 6 of one, half dozen of the other on the method. I prefer the moles method, but that's me. I don't care which method you use. All right? We're going to do the last one, and I think doing the moles on the last one makes more sense to me. Okay? So, how many grams of NaOH must be added to 250 mils of a 0.15 molar HCl solution so that the resulting OH minus concentration is 0.02 molar? Assume no volume change. All right? Because NaOH is a solid. So, first thing you got to do, how many moles of HCl do you have? And well, first thing is, are we strong acids, strong bases? Yes, because it's all we're doing right now. So, moles of HCl is equal to the concentration times the volume. There's my moles of HCl, which means moles of H plus. I don't have to write out the dissociation thing anymore, right? Can we all assume we understand that if it's a strong acid and I know the moles of the acid, I know the moles of the protons. Okay, figure out the moles of... Okay, so actually we have to do a thinking thing here. So, I know. We're adding NaOH to a solution of HCl. So assuming I just want to neutralize the solution, how many moles of NaOH do I need to add? Same amount, right? To neutralize, all right? So To neutralize, we need 0.0375 moles of NaOH. Okay? That makes it neutral. So the pH in that is essentially 7. But we don't want, but we don't want to neutralize it. We want to have an excess. We want a concentration of NaOH to be, or OH minus ions to be 0.02 molar. So then you have to ask yourself, how much do we have to add to get to 0.02 molar OH? All right. So we need this much, plus we need X amount of NaOH to get to 0.2 molar. Okay. So all we got to do is say, well, how many moles of NaOH in a 250 molar or 250 ml solution will give us 0.02 molar concentration? So we just go 0.02 molar times the volume equals 0.050 moles of NaOH. So if I just have pure water and I add 0.0050 moles of NaOH, that'll produce a concentration of 0.02 molar. Okay? But we also had to add in enough NaOH to neutralize the HCl. So how many moles did we actually add? Just add this to that. Okay? Which gives us 0.0425. And then, because you don't measure out moles, you measure out grams. Just do a conversion. So it's 0.0425 moles of NaOH is needed. 1 mole of NaOH is 40.0 grams, which gives us 1.7 grams needed. We went through that very quickly. Does that make sense, the process? All right? So just figure out how much you need to neutralize it, whatever it is, the acid or whatever. Then figure out how much more do I have to add to get to that concentration. Add the numbers together, and you're done. That's a pretty standard test question, okay? You can now finish the package 7 to 9. Tomorrow we'll talk about pH, which brings back everybody's favorite thing from Math 12, log.